Welcome to This Explainer. Today we're diving into a topic that is just fascinating but also incredibly urgent, the quantum threat to encryption. Look, every single day we rely on these invisible mathematical locks to keep our private messages, our bank accounts, and even our most sensitive national secrets safe. But what happens when the ultimate safecracker is finally built? Well, let's jump right in and explore exactly how these digital fortresses are constructed and how a massive revolutionary leap in physics threatens to tear them all down.
Now you might be thinking this sounds like something straight out of a sci-fi movie, but I really want you to consider this. Is your secure data already waiting to be unlocked? Because the reality is, the threat we're talking about today isn't just some hypothetical problem for the distant future. These vulnerabilities exist in the encrypted data that is flying across the internet right this very second.
So, here is our game plan for today. First, current defenses RSA and ECC. Second, the ultimate safecracker, quantum computers. Third, harvest now, decrypt later. Fourth, building post-quantum cryptography. And finally, Part 5, the race to migrate.
All right, let's start with Section 1, current defenses, specifically RSA and ECC. To really grasp the threat, we first have to understand how our digital fortresses are actually built.
Modern public key cryptography is founded on this concept called a trapdoor function. This is basically a mathematical operation that's super easy to compute in one direction, but almost impossible to undo. Think of it like mixing paint. Slapping blue and yellow together to get green, super easy. But trying to take that green paint and perfectly separate it back into pure blue and pure yellow, incredibly difficult. In cryptography, a really good trapdoor function needs a massive gap, a huge spread between the easy direction and the hard direction.
Right now, we build these trapdoors using two major mathematical systems. First, we have RSA, which relies on integer factorization. It's incredibly easy for a computer to multiply two massive prime numbers together, but it is astronomically hard to take that resulting giant number and factor it back into its original primes. It's a bit like how an analog clock wraps around numbers to keep them in a valid range. Then, on the other side, we have ECC, or elliptic curve cryptography. This one relies on the super complex math of elliptic curve equations. But here's the catch. Both of these systems completely rely on the fact that traditional computers simply do not have the processing power to guess the answers in any reasonable amount of time.
And that brings us to a magic number for real-world efficiency, 228 bits. See, as computers get faster and faster, we have to keep making our cryptographic keys longer to keep that trapdoor secure. But ECC is actually vastly more efficient than RSA. It gives us a significantly more secure foundation using much shorter, faster keys. And that is absolutely vital for low-powered devices, like the mobile phones we use every day.
I love this comparison to really illustrate that efficiency. Cryptographer Arjun Lenstra came up with a global security metric. Think of it kind of like a cryptographic carbon footprint. Breaking a 228-bit RSA key takes less energy than it takes to boil a single teaspoon of water. But breaking a 228-bit ECC key, you would need enough energy to boil literally all the water on Earth. To get RSA to match that level of security, you need a massive 2,380-bit key. So ECC is for sure our current gold standard. But there's a storm brewing.
Which brings us to Section 2, the ultimate safecracker, quantum computers. This is where we really need to focus. How exactly do these machines threaten those incredible RSA and ECC trapdoors?
Well, traditional computers use transistors, right? They run on ones and zeros, processing information sequentially. They check one possible factor at a time. It's like checking one universe at a time. But quantum computing exploits the bizarre physics of superposition using spinning particles. This allows those bits to exist as both a 0 and a 1 simultaneously. So theoretically, when a quantum computer tries to factor a number, it's as if it's checking multiple universes all at once. One checks division by 2, another by 3, another by 4, all at the exact same time. By checking multiple universes at once, they can completely bypass the extreme difficulty of integer factorization or elliptic curves.
And the specific weapon that leverages all that mind-bending physics? That's Shor's algorithm. While a classical computer might take literally millennia to brute force a strong RSA or ECC key, a quantum computer running Shor's algorithm could theoretically reduce that effort to just seconds. It efficiently factors large integers and computes discrete logarithms. In short, Shor's algorithm makes constant-time factoring a reality, which renders both RSA and ECC completely broken. The trapdoor is blown wide open.
And that leads us into Section 3, which is honestly a bit sobering. Harvest now, decrypts later.
Because here's the thing. Adversaries are not just sitting around waiting for someone to finish building a quantum computer to start their attacks. No, they are actively recording and storing our encrypted data right now, today. They're just sitting on it, waiting for the quantum capabilities of tomorrow to come online. And once those machines exist, they will just retroactively decrypt everything they've harvested. So the threat to our current data is absolutely immediate.
So what's most at risk here? Basically, highly vulnerable, long shelf life data. We're talking about things that still need to be secret 10, 20, or 50 years from now. National secrets, intelligence, our private health records, highly valuable industrial intellectual property, and critically, military software and firmware signing. Think about it. If a satellite is launched today, its firmware signatures absolutely must be secure against a quantum computer in, say, 2040. But, thankfully, the cryptographic community is fighting back. Section 4. Building Post-Quantum Cryptography, or PQC. We are designing completely new mathematical vaults whose security relies on problems that are believed to be hard for both classical and quantum computers. This is really the culmination of a massive global effort. Back in 2016, the U.S. National Institute of Standards and Technology, NIST, launched a rigorous, multi-year open competition to find these new quantum-resistant algorithms. After multiple, brutal elimination rounds testing for security and performance, NIST finally announced the winners in 2022 to form the core of our future standards. To avoid the vulnerabilities of factoring and elliptic curves, these cryptographers had to find entirely new hard math problems. You can see those foundations categorized here. 3 of the primary winners, Kyber, Dilithium, and Falcon, are based on what's called structured lattices. Kyber is fantastic for general encryption because it's got small keys and it's incredibly fast, while Dilithium is the go-to for primary digital signatures. But actually, just in case that lattice math ever gets broken, NIST also standardized hash-based schemes, like Sphinx Plus, to act as a highly conservative, totally different mathematical fallback.
Okay, so we have the math. Now comes the really hard part. Section 5, the race to migrate. How on earth do we get the entire internet to switch out its locks?
Well, this massive update is operating on a very tight timeline, and it's being driven heavily by governments. NIST announced the winners in 2022 and got basic standards published by 2024. But take a look at 2025. The NSA is already mandating that certain applications for national security systems must start using PQC this early, specifically for software and firmware signing. The ultimate overarching goal is that by 2035, all vulnerable systems across U.S. federal agencies have to be completely transitioned to quantum-resistant solutions. The 2020s are quite literally the decade of urgent action.
Because governments and businesses rely so heavily on open-source software, the readiness of major cryptographic libraries is just vital. Right now, heavy-hitting libraries like OpenSSL, Bouncy Castle, and WolfSSL are already showing full support or at least have very clear implementation roadmaps for these NIST standards. And this is a game changer because when a core library like OpenSSL updates, that change cascades down, allowing thousands of applications, VPNs, and servers to enable post-quantum security with just a simple software update. So, the absolute most crucial takeaway from all this preparation is the concept of crypto agility. The cryptographic community isn't just preparing to swap in one specific algorithm and call it a day. No, they are building systems that remain flexible. If a brand new quantum technique breaks a lattice-based algorithm tomorrow, we need the agility to instantly swap over to a hash-based fallback. We just can't rely on a single lock forever anymore. We absolutely must be agile.
Which leaves us with this final thought. What happens when a new technology renders all of our current internet security completely obsolete? As we've explored today, the threat of quantum computers using Shor's algorithm to shatter RSA and ECC is mathematically real, and bad actors are already harvesting our data in anticipation. The new post-quantum locks have been invented, and the race to implement them is already underway. So the only question left for us is, are you ready to upgrade? Thank you so much for joining me for this explainer, and stay secure out there.